Bismillahirrahmanirrahim. In this interaction, we will learn what is transmission angle for a 4-bar mechanism and how is it important when you are designing a 4-bar mechanism. In this video, we will talk about the definition of transmission angle in the beginning. Then I will tell you what is the importance and significance of this transmission angle for a 4-bar mechanism. And then we will drive the extreme values of transmission angles for various Grashof and non-Grashof 4-bar. So dear students, let's see a 4-bar mechanism quickly. In this mechanism we have this link number 2 and this is link number 3, which is the coupler, and link number 4 is the output link. So driver link or input link is the one which takes the force or torque and moves the mechanism, and link number 4 is the required link which will give our motion. So this included angle, which is shown as mu here, is the transmission angle, and it has a important features when you are talking about the how much the force moved from link number 2 to the output link number 4. So how can we see this force transmission? We can see if we do a force analysis of this mechanism. So here you can see this is torque 2. So torque 2 is applied on link number 2 from the ground link. So the ground link is moving the link number 2 with the torque T2. The torque 2 will apply a force on 3, and that force will be transmitted to link number 4, and we call this force as F34. And if this mu is the included angle between these two links, so this force will have two further components if we try to apply the force on link number 4. One force will be along the tangential direction and the other force will be along the radial direction. This radial direction can radial force can be in the tensile direction or away from the link 4 or towards the O4 point or compressive in nature. So this component of force will not cause any motion. This force will cause other things which will be explained in other parts of the course, but they are out of the scope of the theory of machines. But this component, which is at 90 degrees to O4, causes the torque 4, which is the required torque we need at link number 4. So this tangential component is important. So maximum tangential component will be achieved when this mu will be exactly equal to 90. So this is the maximum one. But as this mu moves from 0 to 1, some maximum value, so this amount of transmission force continuously changes as this link number 2 is rotating. So we are interested to know that how to calculate the transmission angle at any position of the mechanism, and then we will also try to find out what is the minimum and maximum values of transmission angle, because we may need to understand them and they should suffice, they should be sufficient for the torque for which we are going to make in mechanism. So if you choose some transmission angle within the mechanism which is so small that our T4 is very small than the required one, when we will not be able to achieve our required output in motion. So let's see first how to calculate or measure the transmission angle for any position of a 4-bar mechanism. So assume that you have done the 4-bar position analysis. If you have done the position analysis, you don't need to do some extra initial calculations for the transmission angles. You can easily get your transmission angle from that. For example, if you have a 4-bar synthesized mechanism and you already have done its position analysis. Position analysis means that you know it's theta 2, the value of the link number, position of the link number 2. You also know the position of the link number 3, which is theta 3, and then you also know that what is the position of your leg number 4, which is theta 4. So you only need these two thetas and your this angle, which initially I don't call it mu, I call it theta transmission by theta TRANS, and I shortly tell you why I'm calling this theta translation as theta TRANS, because first you have to see that this angle always will be equal to the difference of theta 3 and theta 4, because this angle, if I see further extend here, is again theta 3. So this angle and this angle is equal, and then this angle, if I extend it here, is nothing but this one is nothing but theta 4. So theta TRANS, theta transmission, should be equal to the difference of these. So this difference will be equal to theta 4 minus theta 3. So as the mechanism will move on, sometimes it may happen that theta 3 will be bigger than theta 4, and sometimes theta 4 will be bigger than theta 3. So you always have to take the absolute value of this angle. The absolute value of this angle will always be same and useful. And if we are really interested to measure the theta translation, this absolute value will give us this value. But every theta transmission is not mu, or the real transmission angle which we are going to take. That will be taken as mu if our value is less than 90. So here I have explained. So if your theta transmission is greater than 90, so you have to take the absolute the acute value, so you cannot use it. So you have to uh, take this value from 180 degree, and then it will be your theta transmission will be called mu. So every theta transmission is not equal to mu. You will always call it mu when it is less than or equal to 90 degree. If this value theta 4 minus theta 3 comes out to be less than 90 degree, so then you have to call it mu. So always remember that mu has to be equal to or less than 90 degrees. So throughout the motion of your mechanism, it will never exceed 90. The theta transmission, however, it can exceed from 0 to 180 degrees. So if it is greater than 90 degrees, you have to subtract it from 180 degrees. And then you will call it theta, then you will call this theta transmission as mu. Okay, so in design, what we are interested in mu, not theta trans. Okay, so why this is important? This is important because the link number 4 can move in either direction. We are not sure in which direction the designer wants to move this theta 4. So this top 4, which I assume to be here, it can, within the same cycle, it can move from in the opposite direction, and in the opposite direction the mu will the theta transmission will change the direction of the force. But here we are interested in the amount of the force transmitted. We are not interested in the direction of T4, torque 4, torque 4. Okay, so that's why we will take always the acute value of theta transmission. Once we have designed a mechanism and we know that what is the value of the transmission angle at any position, but what we are more interested in is the minimum value of this transmission angle, because that will give us the position where the minimum amount of force is being transmitted. For a Grashof crank rocker mechanism, for minimum transmission angle, we can look for the two positions. The one position is the that position where link number 2 is overlapping with the ground link, and in this way we can look for the minimum transmission angle. Another position is when this link number 2 is again collinear with link number 4, but this time it is extended. So these are the two positions of the mechanism where we can look for, we have to find the minimum transmission angle mu in these two positions of the mechanisms. And when we put our mechanism here in these two configurations, the mechanism takes a triangular configuration if you ignore this extended portion. So if I try to depict this triangle, either this is a triangle, okay, and or we have this triangle. In these two triangles, the base, this length in the left side, or the extended way is if we call this as A, this as B, this as C, and this as D, this length number 4 as D. So this length, particular length, will be equal to D minus A. And in the extended way, this length will be equal to D plus A. Okay, so now in this triangle, we know all the three side lengths, and also this extended angle is the mu, and this is the minimum view. So either this one left side is the minimum or the right side is the minimum. So these are the mu values, and this extended this corresponding angles are the same angles. So we also know the angles now. So if you know one angle and three sides, you can easily find this angle using the law of cosines. And what is the law of cosines? Law of cosines tell you that you have to take the sum of if, for example, if on the left side, if I make a triangle, on the right side I make a triangle here, and this is the theta, and this is let's say A, B, and C. The law of cosine say that cos of theta will be equal to the sum of the lengths, these two lengths, like B square plus C square, and minus the sum of the third length, which is A, and divided by 2 times product of the first two lengths. So this is the law of cosines. So using the same law, I can calculate the mu angle here for both configurations. So if I look for the left one, this cos will be equal to this left one I call mu1, and this right one I call mu2. So in mu1 we will take the cos of mu1 equal to b square plus c square minus this d minus a square divided by the product of bc to bc. So this is the law of cosines for the left figure. On the right side, the law of cosines is again this one, and we assume that this in this side, if the angle is coming out to be more than 90 degrees, because we assume that in the extended position this mu will be greater than 90 degrees, so we will be subtracting this value from 180, because we already know that mu has to be less than or equal to 90 degrees. So this value here is this, from here to here, this is our theta transmission. So we are taking it to be greater than 90 degrees. Okay, so what will be the minimum transmission angle in Grashof crank rocker mechanism? It will be the one which is giving the minimum of these two values. So if you have already designed a crank rocker mechanism and you are not sure which is the minimum transmission angle, you have to look for these two extreme positions, and using these values you can easily calculate the mu1 and mu2. So from here we can see how to measure or find out the minimum transmission angle mu for a Grashof crank rocker mechanism. So when you are looking for the minimum mu for non-Grashof triple rocker, you have to look for the toggle positions. So if I call this shown mechanism as a triple rocker mechanism where it is non-Grashof, so I name another angle here, this one as mu, nu, or you can call V for convenience here. So when there will be toggle positions and link number 2 and link number 3, which I call them A and B, when these will be linear, the velocity this will be equal to 0. So this angle mu will automatically become 0 if I take its acute value. So 180 will be considered as 0. And this value will be the minimum mu. Okay, so in this way, uh, these are the toggle positions where we'll be getting the mu minimum. In the other two positions of toggle will be the those positions where this link and this link will become collinear. And when these two links will become collinear, automatically this mu will be either equal to 0, or it will be equal to 180, which again will be considered 0 because we are taking the acute value. So the first minimum mu in a non-Grashof triple rocker will be equal to 0 when link number B or 3 is collinear with link number 4. So when 3 and 4 are collinear, we will be calling these as uh, 0 value of mu, but there will be some value of nu in that case. So first minimum is 0, and the figure you are watching here is the second minimum of mu. That is the situation when we can have the toggle, but here link number 2 is collinear with link number 3. So we have some value of nu, 0 value of nu, but we will have some minimum value of nu. Okay, and this minimum transmission angle will be again calculated using the law of cosines. And if I see law of cosines this length will be a, this will be b, this is again c, and this is d. Okay, so the equation in this will be very interesting. So let's see what we have learned. If B and C are collinear, minimum transmission angle mu will be 0. Okay, and the second minimum will be the one where we are looking for nu as 0. Okay, so at nu at 0, we have this position which is in cyan color. Okay, and for this one, if we apply the law of cosines, this 2 times C and a plus b is the product of the other two lines, included lines of the angle. This angle is basically this angle. This is the minimum mu, and this is the numerator from the law of cosine. So sum of the two sides minus the square of the third line. All numerators are squares. So okay, so this is the law of cosines for a situation where we have a non-Grashof triple trigger, and this mu is the second minimum mu. Okay, for the first minimum you have to look for the values where b and c, and that would be obvious because when you are designing a triple rocker mechanism, you already know that when b and c are collinear, there will be no force transmission, 0. And when the other two lengths are collinear, that's length number A and B, then you have this value of minimum. So this is the amount of the force that would be transmitted when you are having these two lengths collinear. Okay, so that's how you can look for the minimum mu, the minimum value of mu when you have Grashof or non-Grashof mechanism. So in the last slide I talked about the crank rocker, and in this slide I told you about the triple rocker. Okay, so if we just sum up the things which we have learned up till now, the transmission angle known as mu is the acute angle between the output link and the coupler, that is represented by mu, and it moves from 0 to 180 degrees, and we always take it from 0 to 90 degrees because of the acute angle. And it tells you about the amount, quality of force and velocity which has been transmitted from one joint to the other one. So its optimum value is 90 degree when it is giving the maximum force transmission, and most of the machine designers make it about 40 degree, the minimum value. There I'm talking about the minimum value of this angle. So 40 degree is something which is used as a thumb rail by most of the machine designers, but you have to look for your own design and you have to calculate your own minimum transmission angle. It should be practically in a way that your mechanism moves smoothly and there is no jerks or extreme accelerations which are causing problems for the long life of your machine. And very important thing, the last point is that this minimum angle mu is important for a 4-bar mechanism when input and output is pivoted to ground. If you are looking for the force transmission or torque transmission for a floating link, like we have the link number 3 coupler in 4-bar mechanism, we use another parameter which is known as JFI, Joint Force Index. This is the measure of the force quality for floating links. So in position analysis, from directly this mu angle, you can see how much is the force being transmitted, giving you the final torque. But for floating links, link number 2, this is not sufficient. You have to do a force analysis, and then you look for the joint force index, and you find the amount of force with this index, which is the quality, force quality, and velocity quality. Okay, so mu is only for lengths which are connected with ground. So that's all for the transmission angle, and you can apply this transmission angle for any 4-bar mechanism you have built which is pivoted to ground. And link number 2 is the input link, and link number 4 is the output link. I hope you have find this video interesting. If you have any questions, ask me and I will try to help you out.